It's taking my Dropbox so long today. It's been on for like 30 minutes. Here we go. Okay, we've got magnetic fields. Oh, just before we do that, I need to fix that one. A battery moving vessel connects to two horizontal parallel plates. One plate becomes positive and one plate becomes negative. An electron is fired at 45 degrees under the negative plate, so that means above the positive plate. At the speed of that, the positive plate lies flat on the ground into a field between the plates. The distance between the plates is not far. I was like, oh, come on. Okay, magnetic field, please. Yes. So, let's have a look. So, a magnet, which you first learn about in middle school. And what exactly is a magnetic field? Again, probably something you learned about in middle school. A magnetic field is the area around a magnet in which there's a magnetic force. So you know when you put the north with the north, it repels, and the north with the south, it attracts. So the magnetic field is the part around the magnet where you can feel the force. Magnetic fields are not, they're short distance. So for example, if this is a magnet, you know from experience that you have to be pretty close before you can feel the force. Magnetic fields don't really go that far. They're quite short range.
Even if that material is big?
It would have to be very big, but even when it's very big, like at a junkyard, the magnet still needs to be at least a meter near the car before it can lift the car up. So magnetic fields, they're really quite short range. So how can you make a magnetic field? Well, interestingly, a moving electric charge can make a magnetic field. So any charge that moves makes a magnetic field. By the way, what do we call a moving charge if you think it back to electricity? Yeah, so a current makes a magnetic field. Magnetic fields can usually be seen by what's called magnetic flux lines. At all times, the direction of the magnetic field is shown by the direction of the magnetic flux lines. So in other words, which way the field is moving, we represent that by drawing these, what we call flux lines. You do need all of this box because there are a few important words in there. So I'll give you a minute if you can write this down carefully.
So is the magnetic field that you should write all of this?
Yes, actually. But the good news is, they don't. Or what I should say is they haven't in the past. They usually, I'll tell you what definition they usually ask when I get to it. But they haven't asked this one before. At least I don't think so. You have all of this happening? Yes. Yes. Okay. Huh? Oh, I must have a really big picture. Yeah. Okay. So, oops, too far. All right. This is, in your definition, I mentioned flux lines. These are flux lines. They show the direction of the magnetic field. So note, please, the magnetic field comes out from the north and loops back to the south. So this is where you would feel the force of the magnetic field. It's only within this region here, this kind of like circle shape. So it comes out from the north and goes to the south. This is, wait. I said I'll tell you when they ask for things in the exam. The last slide, I don't remember them asking for this, but I do know they like to ask students to draw this in the exam. So this, the flux lines on a bar magnet, yeah. This is called a bar magnet. You drew this out now? Let's see. Could turn the page a little bit towards me. Okay, it'll need to be a bit better than that in the exam. Yeah, a few more lines. Yeah. Okay, Musharif, you got that? Now, there is a very important magnet in our day-to-day lives, which is the Earth's magnetic field. So within the center of the Earth there's a giant magnet that runs from the north to the south. And the north of the magnet is down here in the south, and the south of the magnet is down here in the north. So around the Earth there's a magnetic field like this. So I know, Sharif, you were saying that, you know, magnetic range is quite short. And even in this picture it's quite short. Yes, true, this is a huge magnet, but the magnet is the size of the Earth. And even though it's so big, it only goes out maybe twice the distance of the Earth. You know, like one is here, so this would be one again and one again. So you would have to be quite close to Earth to feel the magnetic force from it. So this is the Earth's magnetic field. Again, if you can draw this with the arrows, please. This is another thing that they don't ask it as much But this is one for the exam.
Yeah, 3D.
No, but you can just draw it like this. You can just draw a circle. Come on. You could draw a circle for the Earth with a magnet inside the circle and then draw the lines around it. You know what I mean?
Can we do?
Once it loads. No, you do it actually.
Why?
Because I'm trying to teach you to be independent.
Yeah, this is the way, the right way.
Well, I can't right now because I have to wait. So you can... Let's see what you drew, Adnan. What's in the center?
Small.
No, the magnet runs the full length of the Earth. So you want a long rectangle. Let's see. Slide it down, please. Yeah, that's it. And then this is south and this is north. Yeah, like this. And there's kind of some lines coming out here, and then there's a couple going out here. So that's what I was just going to draw. Nah, it just is used for old-fashioned GPS navigation, but it's not used anymore because all the GPS now is done by satellite GPS. It used to be used, but I can't imagine any plane nowadays using the magnetic field.
No, I meant like the speed.
No, it doesn't affect the speed.
I think
No.
no, because you're already in the field.
Yeah, we're already in the field right now. It's not like when you're in a plane you enter the field. We're always in it all the time. So we can't. Yeah. Some animals can sense the magnetic field, and this they can use to help guide them north, south, east, and west. So some birds can feel which way is north, south, east, and west from just feeling the magnetic field. So they have something in their body, a sense, where they can kind of know which direction to go. Just like how you have eyes, you can see which way to go. They have something inside them which gives them the ability to feel which way to go. So you know the way...
Spider-Man.
Exactly, the Spider-Man sense, if you will. So you know the way sometimes birds fly south for winter and north for summer or whatever. They have a feeling for which way is north and south from the Earth's magnetic field. You know, so they know when the weather gets bad, they feel the need to fly in a south direction against the magnetic field. So I just think that's interesting, you know. So it's important, more important for animals than it is for planes. Okay, did you draw that? Yep. Now apparently some people are supposed to be able to feel this, but I don't think that's true.
Who?
Like, I've heard of stories where some people are supposed to feel which direction is north from the magnetic field, but I don't think that's true. I've yet to meet someone who says they can do this.
Like you can...
You can you can just go like, this way is north. Yes, it would be, but I don't think it's true because there's nothing... I just don't think it's true. I don't think so. I'll have to meet someone who can do this, but I haven't yet. Now, earlier, Adnan, you were saying that a moving charge is also called a current, as you remember from electricity. And a current can make a magnetic field. And here's an example. In this picture here, there is no current. I is 0. So all of these compasses, you know compass, it points north. All of these point to the north. However, when the current is on and moving up, they all point in a circle. Meaning, when the current is on, there's a magnetic field circling around the current. And you can find the direction of the current using something called the right-hand rule. So if you put your thumb in the direction of the current, like this, then this is the direction of the magnetic field around the current. So in the picture here, if I put my thumb in the direction of the current, then the magnetic field is going around like this, using the right-hand rule. Yeah. So it's going, spinning around it like that, yeah. This is another one for the exam they ask you to draw. So in the exam, sometimes I'll see people going like, you don't need to draw this one. This one is what I care about.
You care about D.
Yes. Who cares about A? The current's off.
So,
Iyad, Mir, if you're watching this, we miss you. Will they watch this later? I don't think so. Maybe I should put into the video a secret message so I know if they watched it or not. You know, if I say something like, I will get you coffee if the next time you see me, you say, yeah, where's my coffee? See, then I'll know if they watched it or not. If I see them and they say, where's my coffee, man? Yeah, where's my coffee, man? And I'll get you a coffee. Don't tell them that now.
No.
We'll see. We'll see. Okay. Did you write that down? Yes? Continue? Okay. There is another way to make a magnetic field. I need to make that picture a bit bigger. Something called a solenoid. I need to explain it. And again, they love pictures in this question in the exam, so this is another one. Before you draw it, let me explain it. Earlier in the lesson, we drew the flux lines for a north-south bar magnet. You have that from earlier. And you remember the direction goes from north to south. If you want to make a north-south magnet using a current, what you do is you take the current, the wire, and you spiral the wire around. And if you want to make the same flux lines as this one here, with north on the left and south on the right, what you can't quite see in the picture, and I wonder if I can make it a bit bigger. I probably need to make it a bit bigger. If you have the current coming down on the left, so if it goes in on the right, so if it goes in on the right, loops around, and comes down on the left, then you'll make a magnetic field which is nearly the same, practically the same as the one for the bar magnet. Here it goes from left to right, so this is like the north and this is like the south. The advantage of this one is, well, actually, what do you think the advantage of using that magnet, the solenoid, instead of the bar magnet? What would be the advantage, do you think? I'll give you a clue. It has something to do with junkyards. You know junkyards?
Yeah.
Yeah? Can you think of an advantage?
to make a bigger field strength.
You could make it stronger, but you can also get a strong bar magnet, so something else.
Weight maybe. The way it looks.
The way it looks, that one looks cooler. Well, think about it. If you have a big magnet and you want to pick up a car and then drop it, you can't drop it with the bar magnet because the magnetic field is always on. But with the solenoid, you could flip the current off, and then when the current is turned off, there's no magnetic field, and then you can drop the car. So in other words, the solenoid has the advantage of being able to turn on and off the magnetic field, allowing you to pick things up and drop them. So for industry engineering applications, the solenoid is a very important engineering machine. It's very, very simple. It's just a copper wire. That's all it is. Now sometimes a piece of iron is put in the center here of the solenoid to make it stronger and more efficient than just having empty space. So often the copper wire will be wound around some soft iron. It just makes it more efficient. Well, I think the reason is the iron is a better conductor for the magnetic field than air. So, in other words, the magnetic field, none of it is kind of wasted in the middle piece. I'm not 100% sure because it's not on the course, but I do remember reading that it's better to have a good conductor in the center because it just makes the field more efficient, so you can make the field maybe a little bit bigger because none of it's wasted. You know. I have it in an electricity. I was reading in an electricity book at home. You don't need to know it for the exam, and in fact, in the exam, usually this is empty anyways. They don't put any iron in it. But I'm just letting you know, if you look at a physics book or a physics website or a YouTube video, often there might be some iron on the inside. This is not this one because we did this one earlier. This one here is one to draw for the exam. Please note the N and the S in the diagram, and that the current is coming down here and going up here, and field lines. It's going to be difficult, but try your best to draw this clearly. So this is a great class. You're just drawing pictures. That's all. No?
All of this and it's only 1 hour.
No, look, I'm only halfway through.
What? You know?
7 out of 18. Slides. More pictures and formulas to come. And more formulas. And more definitions. Your favorite. Yeah.
What is the material inside the copper? Magnet.
No, it's the field lines. It's empty space, but
Can I
there's.
make it in Minecraft? Can I make
You should draw some field lines in the middle. Here, there's no field lines because there's the magnet. Well, I suppose they're inside the magnet. It's on the top of the slide. Continue. Did he say continue? So, we saw two things that made me clarify, and that is, what was the last picture? Well, I've already talked about that, so I don't need to say that. And we've already talked about this. I don't know if you wrote it down. It's called the right-hand grip rule that we were saying earlier. I don't expect you to draw this. It's a bit hard to draw. But could you at least, for your notes, write down the name of the rule beside the picture earlier? Right-hand rule. Right-hand grip rule. So what's this now? 9 slides of pictures so far. We'll have to get to another definition. Continue? Possibly? No. So the definition of a solenoid. A solenoid is a coil wound into a tightly packed helix. A coil is this shape. Well, sorry. Coil is a noun, and it means like a spring. You know, spring shape. Helix, do you know this name? Helix is a noun, and it's the name of this shape that goes like this.
Spring.
Huh?
Spring.
Yeah, I suppose what's the difference between coil and what's the difference between helix? So the difference is, helix is the name of a spring's shape. Coil is the name of a spring. So it's like this is the shape's name and this is the noun's name. Like, for example, here. What shape is the door? The door is a rectangle. So, helix is like the word rectangle. It describes the shape. But if I said to you door, you know what shape a door is. It's always a rectangle shape. So, coil is like door. It's the name of the thing.
And
Whereas,
it's obviously like.
and obviously, yeah. So a coil is the noun for the thing, which, like you're saying, is obviously then a helix, which is the name of the shape. Continue? Now, so far, we have said absolutely nothing about the units here. How to measure the field strength and things like this. So when we had electric fields, we had units like newtons per coulomb and things like this. So what are the units here for magnetic fields? We need a way to measure how strong the magnetic field is. Some magnetic fields are stronger than others. For example, the magnetic field at the junkyard would be very, very, very strong. What would be an example of a very weak magnetic field? Little magnet for the fridge, maybe. There is something smaller than that in your day-to-day life. In this room right now.
We are men.
No. The Earth's magnetic field. The Earth's magnetic field is very, very weak field. Very weak field. So we need a way to measure the strength of a field. And we use something called the magnetic flux. Well, sorry. Before I give you the unit, what is it that you're measuring? Magnetic flux. It's a bit like strength. You know, if this is big, it means it's a strong magnet. If it's small, it means it's a weak magnet. So the magnetic flux over a particular area of space is the number of magnetic field lines passing through that area. So just before you write that down, let me just draw what that means. So let's imagine here you have a magnetic field, north-south, and I draw the field like this. And let's say this area is here in space. You would say here the flux would equal 2, because there's two flux lines going through it. So the unit for measuring flux is called the Weber, and it's like me just saying here are 2 Webers, 2 flux lines for this piece of area.
So they're always like the same being?
What is the same line?
No, one is going above another, so it's not so.
Yeah, and then
Is it like stronger because it's longer?
Webers are not the best way to measure strength. We'll have another way. But notice what happens if I make the area bigger. So do I have more flux or less flux? Well, what would it be now? It would be 3 Webers, because there's 3 lines going through it. And what about if I draw a little area here? What would be the flux here? 1 Weber. So the problem with using Webers is if you just make the area bigger, then you'll have a bigger number. So it's more, for this it's important how big the area is and where it is. Like for example, if I put it here, then I have 0 Weber. So it depends on the location and the size, you know. So we have the Weber is the SI unit, which is the same as, although you don't need to know this for the exam, but it's just interesting that the Weber is the same value unit as a volt second. But this is not something for the exam, it's just as a matter of interest. So we won't use that, we'll just go with Weber is the unit for measuring magnetic flux. And this is the symbol for magnetic flux. Yeah? You happy with that, man? Okay. Now, you realise that, okay, well maybe instead of using magnetic flux, maybe we should look at the magnetic flux per unit area. So for example, rather than using different areas, maybe we should look at it for the same amount of area. So this gives us the idea of something called magnetic flux density, which is the magnetic flux per unit area. Per unit area. So as a formula, what would the formula be for magnetic flux density? Yep. Over area, yeah. So the unit is called the Tesla, which is just Weber per meter squared. And as a formula, like you said, Adnan, is flux over area. The B, magnetic flux density, is the nearest thing we have which is like the E for electric field. So a big E means a strong electric field, a big B means a strong magnetic field. And I said I'll tell you when I give you a definition that they ask for in the exam, and this one is the one that they ask the most. The definition of magnetic flux density. Now, the magnetic flux density is always measured perpendicular to the field. A bit like pressure. Got it? Okay. Okay. So, a moving charge will produce a magnetic field. And by using the right-hand rule, we know what this field looks like. If this moving charge is in a magnetic field, then it will feel a force. Remember from middle school and life, north and north push away, north and south attract. Yes. So, you know, if I have an electron moving from left to right, which way is the current? Yeah, so there's a current going this way then. Using the right-hand rule, yes, the magnetic field is going around this way. Yeah. So it's yeah, hang on. It's going around like this. Oh, that's terrible. But you get the idea. It's coming. It's coming towards you as it loops around.
It's going that way.
Yes, well, you get the idea. So if we look here, for example, it goes from north to south. So imagine that there was a magnet here, south, north, and the magnetic field is moving down here from north to south, and this is going from north to south, and there'll be a force pushing away, you know. Anyways, I don't want to talk about this diagram because it's not, this particular one is not on the exam, and it gets very complicated because you're moving in 3 dimensions, so there's a lot happening on it. But what I do want to give you is the formula which tells you how much force you will have. So there is a force on a charge that's moving in a magnetic field where the flux density is B and the charge is moving at V. You might wonder, why is it important to know the velocity? Well, if the velocity is 0, the charge is not moving. If the charge is not moving, then there's no current. Yeah, and if there's no current, there's no field, and if there's no field to push against the other field, and so there's no force. So it's not surprising that the V is here. The formula for the force is QV cross B. Now, cross means multiply, but it's a special type of multiply which I'll explain. So force in a magnetic field, force experienced by a particle in a magnetic field with charge Q, velocity field V, and density B is given by this. Cross is a special type of multiplication known as cross product. The cross product is a multiplication of vectors where the result is found using Fleming's left-hand rule, which I will show you on the next slide. What's that? No. No, trust me. Continue. So, if you look here, you have F equals, I should really figure out what Q's I'm wanting to use. Q, V, B. The Q is scalar or vector? Scalar. The velocity, scalar or vector?
Scalar.
Vector. B, vector or scalar? Vector, because it's the lines, so there's a direction to it, yeah. And force? Vector. So this cross product, what the heck does it mean? So if I say vector V cross vector B, well, that will just be a vector of size magnitude of V multiply magnitude of B. And you might be thinking,
That's just the math x1, x2 plus y1, y2 plus.
yeah, so let's just say, I don't know, this was 10 meters per second north, and this was 2 Tesla east or whatever. The cross product would be 20. So you might be thinking, okay, Stephen, this seems like regular multiplying to me. You just multiply the numbers. But what I haven't shown you is how to get the direction. How to get the direction, because this has a direction. And we can get it using the left-hand rule, which I'll show you on the next slide, but I'll explain now. You have the formula? Okay. So, in the formula you had 3 things. 3 vectors. F for force, V for velocity, and B for the magnetic field, the density. So, what you do is, you have V multiply B. So this is like the V, the velocity, the direction of the current. And this is like the B, the direction of the field. So this one is field, and this one is current. This will be where the force will move. So for example, if the field goes into the board, and the current is moving to the right, then which way will the force be moving? Pushing. There'll be an up force on the particle. What about if the field is heading to you, and the current is heading to the door? So the magnetic field is moving towards you, the current is moving towards the door. Which way will the force be on the current? Well, let's check it. This one here is field, which I said is to you. Current is which way? To the door. So I must turn my hand like this, because this points where the current is pointing. Field to you, current to door, so the force is down.
No?
This is wrong, because
The field.
the field is going to you, so you have to point yes, and the current is going to the door. Turn, yes?
So,
Turn your hand upside down.
But this is the idea, you have to turn your hand.
Yeah. So therefore the force is down. Yeah?
So the exam you have 2 choices. You up or
No, because you could have, like, for example, let's say the magnetic field is going down into the ground.
And the current is going.
So the magnetic field is going down to the ground, and let's say the current is going out the window. So which way is the force? To you. No, the field is going down to the ground.
So this one.
Yeah.
Down.
And the current is going to the window.
This is the current.
So the force is going towards you. To you. This is called Fleming's left-hand rule. It's for calculating the direction of the force in the field. Yeah. Try to draw this in your notes. Try. You drew a beautiful hand?
Yeah.
Really?
It is.
Great, it's great. Okay, continue.
Yeah.
Right, now ready for our first question. A bar magnet has a flux of 2 Webers, and the region is a circle of radius 1. What is the flux density? Okay, what's the formula for flux density?
B equals flux over area.
Yeah. And I tell you, it's how many flux lines?
2.
2 Webers. And the shape, I said, is a circle of radius 1 centimetre. So, yeah, so it's 2 over pi or squared. Can you just hit that in and give me the answer? How many Tesla will that be? Six. 0.2 Tesla. Now, in real life, you never get answers this big. They're usually small things like millitesla. Okay, next one. That was an easy one to get started. Next one. A proton moves towards the east in the Earth's magnetic field. What direction is the force due to the field? Okay, so we'll have to draw this one. North, where Santa lives. South, where penguins live. East, where's Mecca. West, where's America. All the 4 important places. Now, which way is the magnetic field? From north to south. This is the magnetic field, which I'll call it B. Which way is the proton moving? Towards the east. So you have a proton moving this direction. So which way is the current moving? To the right. So we want to know which way will the force be on the proton. Well, that's left-hand time. This is the field, so that goes down in my picture. And then this is the current, which goes east.
The current is going down?
No, the current's going east.
Why?
Because I said that in the question.
And when it's going down? Okay.
No, you're looking from the sky. You're looking from the sky. Looking down at the picture.
And you only know...
You're looking at it like a map.
Yeah, and you only know that going to the east.
Yes.
The current.
Yes. Yeah. So the force will be into the page.
Yeah, but you have to know 2 things to get this there. Like, you know the current.
Yeah.
Going to the east.
Yeah.
What is going to? What is the field?
Going from north to south. Because it's the Earth's field. What?
So it's like this.
Guys, look, this is the field.
Okay.
Oh wait, hang on. I wonder if I did that right. So, yeah. No, sorry, I drew that wrong. Because, remember in the picture of the Earth's magnetic field? The magnet is here, and this part of the magnet is south, and this part is north. So the field is going this way. So I should have drawn my blue arrow pointing up, not down. Alright, so what did you get here? Field, up. Current, right. So force to you. So the force is coming out of the page. Now there is a symbol for out of the page. Yeah, which is which? One is for out and one is for in. So this one is for out and this one is for in. So if I draw this, and then I draw this, the force, I should draw it like this. It's coming to me in the picture. Yeah? Okay.
Can you go back?
Got that? Continue.
Yes.
Right. This is the last example, which is the more mathematical one. An electron moves in a magnetic field. The magnetic flux density at the location of the electron is about 250 millitesla. The electron is moving at 1/10 the speed of light. What is the acceleration of the electron? Okay, so here's an electron. It's moving in a magnetic field. The magnetic flux density at the location of the electron is 250 millitesla. The electron is moving at 1/10 the speed of light, so its velocity is 1/10 c. What is the acceleration of the electron? So the electron is moving in a magnetic field, and there's going to be a force on it. Now, in the question, I don't actually care about which direction the force is. I don't care. I just want to know how much the force is. So it doesn't really matter, but just to make it easier, I'm going to draw the force this way as well. So if we work out backwards, well, you know what? Hang on. Let's put the current. Is the current going left or right? If the electron's moving right, it's going left. So that's this one. So if I put the current going that way, it will be easier for me just to say that the field is heading to U, because then which way is the force? It would be up. So what I'll do is I'll say the current, this is the current, and then the field I said should be heading to U, so I'll draw the field like this. So then the force will be up on the electron. So what will happen to the electron here? Which way will it move? Well, it's trying to move right, but which way is the force? Up. So what path will the electron take? Yeah, it'll actually kind of go like this. Shoom, it'll swing up because there's a force pushing it up. You know, imagine something was coming towards you, and then all of a sudden you push it up. It will swing up. Yeah. We want to calculate what this F is here. Okay. So formula is F equals ma. Do I know the m? Yes. Do I know the a? No. What formulas do I know? Well, earlier I gave you this formula, F equals Q V B cross B. So if I make these equal, I get MA equals QVB. Do I know the M? Yes. I want the A. Do I know the Q? Yes, it's the charge of an electron, so I know it. Do I know the V, the speed of the electron? Yes. And do I know the B? Yeah, so I know everything. So I can get the answer. V will equal, A will equal QVB over M. So if I just take out the old calculator and hit that in and see what I get. Fraction on the bottom is mass of the electron, which is constant number 3. On the top is the charge of an electron, which is constant 23, times the speed of light. Oh, I don't know which constant it is, but I think it's roughly 2.99 times 10 to the 8. multiplied by 250 milli.
And then the C, so you have to divide by.
Did I not put in that? I did, see 0.1. You can see that there? Yeah. Okay, let's get the A. Huge number, 1.3 times 10 to the 18. Now you might think that's kind of too big, but you must remember magnetic fields are very, very short. So very quickly this will leave the magnetic field and no longer feel this force. Yeah, so it'll just be, do you know the English word here for describing what's happened to the particle? We don't say it's being pushed out of the field. There's another verb. I'll help you out. The field has blanked the electron and not pushed. True, the field has pushed the electron, but there's a better word here. Knocked out? Yeah, I like it. The field has knocked the electron out, but one word here.
No.
Not knocked. Begins with a D. De-knocked. Deflected. The field has deflected the electron.
The 250, is it the mega or
Milli, sorry. This is normal because usually it's quite small, the Tesla. So it's quite usual to use millitesla or sometimes microtesla.
So how can I write the mega? Is it the
Capital M. I just want to make one small change here to something when you're ready. Continue? Yeah. Adnan? Okay, let me just check one thing here. So let's have a look at the questions. Okay. 4 questions, Musharif. Should make you happy. I just want to make a change to the one we just did. Electron enters a magnetic field and then experiences a deflecting force. Huh? Yes, thank you. A deflecting force. The magnetic flux density at the location of the electron is about, on average, 215 millitesla. The magnetic flux density at the location of the electron is on about average 250 millitesla. The electron is moving. The electron was moving at 1/10 the speed of light when it entered the field. What is the acceleration of the electron due to the field?
I think there was 2 mistakes.
Yeah, no, at some point over the summer I had to read through all my slides again and fix the typos. It's the physics I care most about. Yeah. Let's see. Okay. There is exactly 1 minute left. Let's sit patiently and quietly for 1 minute and then we can go. You think I'm being serious, don't you?
No.
What classes have we got tomorrow? We have maths in the morning, but do we have physics after lunch? We have something in the morning. We always have something in the morning, Monday to Thursday. It's probably maths. Wednesday. Do we have physics after lunch?
No.
So it's just maths tomorrow.
Yeah.
And we'll have physics on Thursday, but not this Friday. But usually Friday. No, I think next week probably would be better for the test. But the only reason I really wanted to do the test is to give you a chance to increase your predicted grade.
For me, so if you do the test, like
No, because after you do the test, you can choose to give it to me or not.
if I
Mine can.
like if I make a fault and I give it to you.
No, you're making a risk then, you know. So maybe it's better not to give it to me. Trust me, the best outcome for me and for you is if you don't give it to me, because that's one less thing to correct. But you agree with this? Yeah. But some students really wanted a chance to prove that their predicted grade was incorrect, and I would like to give them that chance. If I'm giving this student this chance, I must give the same chance to everyone because I'm a fair guy. But you don't have to take it. It's an option. And personally, I would prefer if you didn't take it because I don't want to be correcting more stuff. Yeah. If you're talking to Mir and Adnan, Mir and Ayad, if you're talking to them, can you please let them know about the plan to move the test next week because you have too much going on this week? If you're talking to them, can you let them know?
Just next week.
Yeah.
We have group like.
Yeah, but if they're not coming to school and they're on WhatsApp and you're like, hey man, how's school? Feeling better? Or whatever way you speak to them on the phone. Just let them know that we might move the test to next week. All right.
Or me.
Well, it's up to the class. So you're only half the class.